Hello, and so today we discuss a very different kind of thing, and whose name is Riemann Zeta function. Okay, so I'm not going over the full details, but I just will give you some overview that what Riemann did to some basic functions and what the great mathematicians they did to very simple problem, and then they extend the problem to some higher domains or not the basic domain. So Riemann Zeta function is kind of like that. So Riemann just did construct a simple function. We can, even any student can see what kind of function it is, but then what Riemann did, that he extend the function which meant to be a function on the real line to a function over the complex number, the complex field. Okay, so let us see that what Riemann did. So this zeta function is kind of Greek letter, which just like this kind of thing. So zeta s, I would say, I don't know why it is s. So it is defined like this: 1 plus 1 by 2 to the power s plus 1 by 3 to the power s plus 1 by and blah blah blah. Okay, so this is thing, you can see that this is a pretty simple thing. And if you talk about the convergence of this, of course here at first we conclude that this s belongs to capital R. And if you just first look at this problem, and this is just a basic graduation mathematics, college mathematics, where if s greater than 1, then this zeta s convergent. Okay, converges. It is pretty basic that if s greater than 1, this means for any point greater than 1, then this series is pretty convergent. Okay, so you can use any kind of ratio test, real number ratio test, or some logarithm test, or even some power test, and you can see that what really going on. But then what happens, that what Riemann did, that he extend this this domain R to the complex number field C. Okay, now you might think that how is this possible, because let's put that s equals to -1, then what zeta of -1 is that 1 plus 2 plus 3 plus 5 plus, so this is a divergent, this is basically a divergent, but this is of course divergent, but you have to think about some extended system. Then you can put some value of this zeta -1 so that this function might be convergent. Okay, but of course when you put some complex number, then the convergence really changes. So what they did, what Riemann did, okay, that he turned it into the field C. But there is only one problem, which is this, that zeta of +1, it cannot be defined. Okay, zeta +1, it cannot be defined. So you have to put some basic values to +1. And if you talk about zeta +1, which is this 1 by 3, 1 by 5, and this, this is basically the series of this 1 by n equals to 1 to infinity, and of course which is divergent, we know. So this point 1, which is indeed the pole, okay, the pole of this Riemann zeta function. Of course the domain is C. And what is pole? Let's say that fz is a function over C, analytic function. So if let's say z0 belongs to C, such that 1 by fz0 tends to 0, okay, then you can see that z0 is indeed a pole. Okay, but of course you have to define the function in such a way that this kind of thing happens. So this is the thing. Now let's plot this function. I cannot plot this function, but let's see that what really matters in complex number system, or some basic properties of this function, that what makes this function really beautiful. Okay, so now erase it off. Oops, my board is pretty dirty because it's too small. Okay, so now let's see that okay, now let's write the zeta function. Very good. So this is like this, n to the power s, where n equals to 1 to infinity. So this is zeta s. So now some basic properties, that the domain of this function is not actually C. The domain is indeed C minus the singleton set 1. Okay, So you have to delete this number 1, because at 1 it is not defined. So as I said earlier that of course for let's say that S equals to sigma plus it, you know, this is just complex. So for this sigma greater than 1 means that real of S greater than 1, then this zeta is good, I mean pretty well defined, okay. But for, you know, this sigma less equals to 1, the function is not that much defined. So what happens, that what Riemann did, that he gives some definition and he extend that function, this function, to which is called the analytic continuation over the whole complex field, okay. So that's what it is, but that function is pretty complex, so I'm not going over that. I'm just giving you some introduction to what is this. Now some interesting fact is this. So many people that heard of the Basel problem in statistics. So and the Basel, I mean the function which generated is that if you put S equals to 2. So if you put S equals to 2, which is zeta 2, and zeta 2 is basically this, so 1 plus 2 square plus 1 by 3 square plus 1 by 4 square and blah blah blah. So 2 which is greater than 1, this means this is convergent, and in that point which is convergent to some number which is indeed pi squared by 6, okay, this can be proved. And some interesting properties, that zeta of minus 2 equals to 0, zeta minus 2 equals to 0, zeta of minus 1, of course if you put minus 1, then it said some interesting properties is that minus 12. And why this minus 12? Of course this is just defined, okay, it is not the natural that this is values minus 1 by 12, okay. So now if you talk about that what is 0, so zeta of 0 is I think half or minus half, yeah, minus half. So these are all defined, okay, but only point which cannot be defined is that S equals to 1, okay. Now what Riemann hypothesis says, that this function has some zeros. So this function has two kind of zeros, which is trivial zeros and non-trivial zeros. So trivial zeros basically lie over the real line, and which is all the even points, okay. If you put all the even points, then this function is basically 0, okay. I mean of course the negative zeros, all the negative zeros, the function is 0, just like this. But there are some interesting properties about this function, is that this function has some non-trivial zeros, okay, not on the real line, over the complex line, okay. So let me see that what is this, okay. So let's put the complex number field. So there is a very beautiful thing, that this line, and this is what sigma equals to 1. We remember that S equals to sigma plus it, okay. So there it is sigma, and there it is t, okay. So there is a middle line here, and this strip, okay, where is the color pen, okay. So in this function, this strip, actually this open strip, of course open not close, this strip is called the critical strip, because the zeros or normally lie on this line, okay. So this line basically, you know, this is the middle point, so this is sigma equals to half. So what Riemann says, hypothesis says, I mean Riemann claimed that all the non-trivial zeros lies over this line, okay. So this is the hypothesis that cannot be proved and cannot be disproved, but of course there are mathematicians who found some zeros, I mean so almost too much of zeros over this line, but there is some range like t equals to 0 to t equals to 300, okay. That's the range that where they found so many zeros. And I think some mathematician, I think the Hardy-Littlewood principle, it says that it has infinite number of zeros over this line, and this line is called basically the critical line, okay. This is called critical line, this line, this is called the sigma equals to half. This is the main thing, and which is in fact the point of discussion of all the mathematicians, what they are trying to do. This is 0, and the most interesting thing, which is this, that yes, the minus 1 lies here, this is minus 1, and at this minus 1 we put the values 12, minus 12, and if we just put the value minus 1 to this problem, which is indeed this, and which is minus 1 by 12. Remember, this is not the proper thing, this is just, you know, it is called the extended version. It is defined that it is minus 1 by 12, and that's why you can see that so many posts and so many YouTube videos that it says this equals to minus 1 by 12, and even Ramanujan sometimes, you know, some kind of things like that he did to this problem. So this is basically what is this. And of course this sigma equals to 1 is also a very beautiful line, because on the right hand side the function, which is normally well defined, and other than that other than that set, I would say the left hand side, the left hand, this closed, I do semi closed left hand side, the function is not well defined, so there is some analytic continuation, and at the point 1, and this is a very beautiful problem, this is the pole, this means the reciprocal of the function at this point is 0. Okay, so this is the thing, and you know what Riemann hypothesis is, so you can go try, but don't try if you don't like this thing, because Riemann hypothesis is pretty good and pretty dangerous thing, because it has some $1 million, it is a $1 million problem, and it is still unsolved, because you have to either prove or disprove that whether all the zeros lies on this strip or not. Okay, people find some zeros, but not all the zeros. Some Hardy-Littler principle says yes, it has some infinite number of zeros, not all about the non-trivial zeros. If you put the negative values, then it is 0, but not that. But Riemann function, Riemann Zeta function is not that much simple what in this video you see, because it has some, you know, I would say critical structure. So in future videos we will see that what kind of things these are. So there are zeta, there are some gamma function relation to this problem, and one of the most important thing about Riemann Zeta function is that it connects the prime numbers. Okay, this means that if you can, you know, exactly find the number of zeros or some kind of things, then for some range of natural number you can find that how many primes are there on that on that range. Okay, so this kind of problem. And as I said earlier, that AC equals to, for AC equals to 2, there is some a beautiful Basel problem which has been solved by Euler, none other than Euler. Euler is a beautiful mathematician. So that's what it is, and thanks for okay, this video is going crazy, and of course this is Sunday, so this means this is fun day.